In the past few weeks, we nearly non-stop talked about our star system. But it's like baking bread without adding the flour to it. Because we've talked about nearly everything except the essence of it all. Although Earth is our home, we do not live in an Earth system. Jupiter, the gas giant, might be the greatest planet of the system. Nevertheless, we don't live in a Jupiter system. We live in a solar system. So the next few episodes will be dedicated to our Sun. As a writer, I like trilogies. Currently, I'm working on the second one. So I plan 3 episodes, but there might be more. As a Leo, I run on solar energy, so our Sun deserves special attention. Even though, in a cosmic sense, our Sun is completely insignificant. It's a simple, main sequence, yellow dwarf, G-type star. Nothing special about it. Without it, however, there would be no you, no me, nothing. So let's power up heat shields and head towards our main source of light. Let's begin with some numbers. The Sun's age is approximately 4.6 billion years. Its average distance from our planet is 150 million kilometers, and this distance we call an astronomical unit. The Sun's diameter is 1.39 million kilometers. To put that into perspective, 1.3 million Earth would fit inside it. The Sun's mass is 333,000 the mass of the Earth. The Sun uses 600 million tons of hydrogen every second. And the crazy part that this fuel is still enough for billions of years. Speaking about numbers, here's a humbling detail. The Sun is 99.86% of the mass of the whole solar system. Everything else, the gas giants, every other planet, asteroids, comets, everything else is just 0.14%. How much do we humans make up of this 0.14%? It's undetectable. And due to this incredible mass, the star has incredible gravity. That gravity keeps the whole solar system in place. The Earth and all other celestial bodies do not orbit the Sun because they are willing to. They are locked in this orbit due to gravity. The Earth is constantly falling towards the Sun, but as it has a sideways momentum, it misses it. The same happens with the International Space Station and all the satellites on low Earth orbit. They are in a free fall towards Earth. But as they also have a sideways momentum, it's not so easy for them to fall until they are captured by atmosphere. What is the Sun, or basically any star? It is a giant ball of plasma powered by nuclear fusion. And what keeps it together? Why doesn't it collapse. Why doesn't it explode? Because two forces are keeping it in balance while the star is in its main sequence, not forever. Gravity presses it. The thermonuclear reactor, which is the core, always pushes the pressure outward. And the balance of these two forces is called hydrostatic equilibrium. And now let's deal with what powers the sun or any other star, that is the fusion in its core. The core's temperature is extreme 15 million Celsius degrees. The pressure is 250 billion times that of the atmospheric pressure of the Earth on sea level. Incomprehensible, right? These extreme circumstances do not allow any matter we know to exist. So there is no gas, no liquid matter, and anything near solid matter. There is a fourth state, the so-called plasma. But in this plasma, even atoms are stripped apart. Electrons separate from the nuclei, and that's when the fusion story begins. The sun uses the so-called proton-proton chains. 4 hydrogen protons are needed. You might think that they cannot interact as they both are positively charged, but they collide with such extreme force. And in these extreme circumstances, that is temperature and pressure, plus a bit of quantum mechanics, they overcome their electrical repulsion and interact. What's the result of this interaction? A helium nucleus. There are also positrons, gamma rays, and neutrinos. Yes, those neutrinos which are almost undetectable, but they are everywhere. They run through your body right this second, but you have no idea they are there. The fascinating part of this fusion is that the helium nucleus is a bit less in its mass than the original hydrogen nuclei. What happens with the missing mass? It is converted into energy in accordance with Albert Einstein's most significant equation, E equal mc squared. Okay, the fusion was complete. Energy is born. And now you might think that the photon produced by this fusion is that very photon you see when you look up at the sun. No. This photon has to make the longest journey towards the surface. At first it enters the radiation zone, where it's absorbed and re-emitted over and over, because plasma is so dense there that a poor photon can barely move without colliding with some other particles. It's pushed everywhere, left, right, up, down. And brace yourself for this. It takes 100,000 years or even more for a single photon to reach the surface of the sun. So that ray of the sun, which is burning us during the heat wave, was born when mammoths were roaming the Earth. It's much easier for neutrinos. They work their way easily through the radiational zone, and they move freely everywhere in space. When the photon reaches the convection zone, it has it easier to move. The convection is something like we all know from heating systems. Circling. But in the sun's case, it is not water that's circling, but plasma. This plasma ascends and cools, then descends again, over and over. Each time the plasma rises, it loses energy. And as I said, it cools. So, starting with these layers, the temperature drops to nearly 6,000 degrees Celsius. And this is when the photon finally reaches the photosphere. That is what we see with our eyes. And its light travels to Earth in 8 minutes and 20 seconds. But a photosphere is not something smooth. It is made up of granules. And these granules are what you see behind me. What did you think? That they were hazelnuts? They might look tiny, but they can be 1,000 kilometers across each. The chromosphere is something that we do not see, as the photosphere is too bright to perceive it. But during total solar eclipses, its reddish layer can be observed. By the way, have you seen the solar eclipse on August 12th? There was only a partial eclipse where I am, not long before sunset, and as I had no flat horizon, that's all I could capture. The chromosphere is that area where temperature starts rising again. It might sound strange, because we would think that as we distance from the core, the temperature should drop on and on. But the opposite happens. And when we reach the corona, something really crazy happens. Temperature is 1 million to 3 million degrees Celsius. The corona is not a layer which stays in place. It extends to kilometers into space, eventually shifting into solar wind. But what makes it be so extremely hot? On the one hand, the sun's rotation is not usual. It's different at the equator and at the poles. Plus, there is incredible magnetism. But that's the topic of our next episode. So subscribe, hit the bell to get notified, and whenever you feel insignificant, think of the sun. There's nothing special about it, yet it's the only star we know as of now out of trillions, which has a planet orbiting it where there is complex and intelligent life.